said, I'm delighted to announce the speaker for today, Christine Lee. Christine is an engineer with more than 5 years of experience in applying data science and machine learning in the healthcare industry. She's passionate about creating technologies that provide meaningful clinical decision support and improve patient outcomes. She graduated with her PhD from UC Irvine in biomedical engineering under co-advisors Pierre Baldi and Maxime Kenneson, where her research focused on applying deep learning to perioperative data. And she previously worked at Edwards Life Sciences as an applied machine learning engineer for critical care and anesthesiology and medical devices. She's currently a data scientist at Brightside Health, focused on helping to improve remote mental health. And today she will be talking about the development and validation of an interpretable neural network for prediction of post-operative in-hospital mortality. The floor is yours.
Awesome. Okay, let me go ahead and share my screen. I should have done that before. Okay, I think that works. Oh my gosh, of course, sorry. I have like a brand new computer and then now it's saying I need to give access.
No worries.
Oh.
You probably need to restart Zoom for a second.
Yeah, sorry. I have to quit and reopen. I'll be right back.
That has happened to me before as well.
Okay, I think that's working now.
Yeah, perfect.
Awesome. Yeah, so I'm here to talk about my work in, this was actually like pretty, this is from my PhD work, so it's a couple years old for me now, but I'm happy to talk about, in the discussion as much as I can remember. So just as a brief overview, I'll start with talking about just a bit about the previous work that we did on predicting postoperative outcomes, that then the follow-up paper that we did was about developing an interpretable neural network. I'll also go over a brief overview of neural networks in terms. I'm not really sure if that's necessary for this audience, so it might just be repeat or just way too simplified for people here. But in any case, I'll just do that really briefly, continue talking about that previous work, and then finish with talking about that interpretable neural network paper. So these are the two references for the work that we did on just predicting postoperative outcomes. So there's definitely a need for prevention of postoperative complications. So more than 230 million major surgical procedures are performed annually. And although the overall mortality rate is very low, it's less than 2%. If you look at how only 10% of the surgical population is at high risk, that 10% population accounts for 80% of postoperative deaths. On top of that, you can see that postoperative complications such as cardiac arrest or sepsis, renal failure, these actually end up being significant determinants of survival. And despite all of this these stats and this knowledge, if you look at who's actually admitted to the ICU, less than 15% of high-risk surgical patients are actually admitted to the ICU. And so there's this need for not only identifying people who are at risk of postoperative complications and mortality, but also that's to help resource allocation. And if you look at postoperative risk scores that are currently available, there's many other scores that have been published on, but I'm just going to highlight these three here. So you have the ASA score, which is the American Society for Anesthesiology score. This was developed in 1963. It is a subjective score. It's really up to the experience of the anesthesiologist who's treating that patient. It's a score from 1 to 5. It just is an indicator of overall health, and it's always given preoperatively. And then you look kind of fast forward-ish, you see these logistic regression model scores that have become really popular. So you have the surgical APGAR score, which was developed or published on in 2007. This is based on intraoperative estimated blood loss, the lowest map of the case, lowest heart rate. They take the regression coefficients, and there's a maximum of 10 points, and that's how they calculate the score. And then you also have what's called the post-POM score. This was published back in 2016. This was developed on more than 2 million patients. It's a preoperative score, and it's actually something that's currently being used at UCLA today. So why are logistic regression models so popular in medicine? Well, especially when it comes to scores, they're really easy to implement, they're really easy to interpret, and they usually have pretty good performance. So if you look at the post-POM specifically, it's a logistic regression model of 17 preoperatively known variables. And you can see here, they learned these regression coefficients. Those regression coefficients are normalized to the coefficient that was learned for age, and that's how you get these post-POM points. So really straightforwardly, they just took the regression coefficients, created the post-POM score. And so even though logistic regression models are really great, we just kind of felt that, well, neural networks and deep neural networks, they're so great for learning complex features and complex relationships, and have been really shown to have higher accuracy than a lot of kind of the more simpler, quote unquote, models like logistic regression. And so we were really interested in, well, what can we do to use deep neural networks on predicting postoperative risk? So the data that we used was all surgical cases performed between March 2013 to July 2016 at UCLA Medical Center. The exclusion criteria were patients undergoing general anesthesia or less than 18 years of age or greater than 89 years of age. We had about 60,000 surgical records total. 80% of that was used for training, 20% was used for test. The labels that we were interested in were in hospital mortality during hospital admission following surgery, acute kidney injury class 1, which was defined as a 1.5x increase postoperatively in serum creatinine from the preoperative baseline, and postoperative reintubation, which was defined as any intubation during their hospital admission, and then if any of the top 3 labels were present in the patient. So in summary, we had about 50,000 patients for training, about 12,000 patients for tests. About 60% of patients actually had no acute kidney injury label, and that's just because not all patients get a serum creatinine lab. But from there, 22% of patients had an AKI class 1 or greater, about 1% of patients were reintubated, and less than 1% of patients in our data set had mortality. In terms of the model features, so actually, if you look at the original paper, we started with something like 75 features, and we found that 46 features of that were reduced was actually giving equivalent results. So we have this 46 original feature set, and this looks at things like descriptive intra-op vital signs. So that would be things like what's your min, mean, max heart rate, blood pressure, et cetera. Drugs and fluids interventions. So things like what was the maximum vasopressor rate administered to this patient, their total amount of fluids, things like also what was their maximum rate of general anesthesia, if it was gas anesthesia, et cetera. And then we also have basic patient info like age, ASA score, as that's something that all patients are given preoperatively. Then we also included 6 mean blood pressure features. So this was specifically the minutes of case time that was spent with MAP, so your mean blood pressure below 40 to 65. And the reason why we added this was because all of this research that had shown that time spent in low blood pressure really increase your chances of postoperative complications. And then from there, we tried to reduce our feature sets just by, if there was a high correlation with other features, we just excluded them. And all of these features were actually chosen just from the clinician's domain knowledge as important, potentially important to postoperative complications. In terms of missing values, I'm sure if anyone's familiar with like electronic medical record data, this happens a lot. There's some values that were purposefully missing, and those were filled with 0. So that's like maximum isoflurane, for example, if they didn't receive isoflurane as their general anesthesia, so that's purposefully 0, versus all others were filled with means. Categorical ASA score missing values, as this could happen, even though it happened very rarely, were just filled with the most common ASA score. So from there, we developed, we tried to look at different ways of modeling. So one is what we called the Deep Neural Network Combined, so the DNN Combined. And that was a model that was trained to output 3 different probabilities, one for AKI, reintubation, mortality. It's not a softmax problem, so it's not, since you can have one or the other, and the other. So this is literally in the model, we split it so that at the end it outputs a probability for each of them separately, but they were trained together so that there could be some kind of learning of the features together. And then we also looked at what happens if you model them individually. So a deep neural network that was trained individually for just the probability of AKI, for one that's just the probability of reintubation, and then third, just for mortality. And then we were also interested in like, how did it predict any outcome? And that was just a simple averaging of the probabilities that were output. We did a 5-fold cross-validation on the training set to select for best hyperparameters, and then we also compared against the ASA score and logistic regression with the same features. And so just to kind of go onto just brief overview. So when we talk about training a model, right, we're just saying what we really want to learn are these betas. So the betas are either your weight coefficient, your model coefficients. Those are iteratively updated in a way of minimizing your error. In the case of logistic regression, this is what the formula would look like. Your betas are your bias and your logistic regression coefficients. And the error is some kind of error between your predicted Y, which would be some value between 0 and 1, and your true label, which is a 0 or a 1 for classification. So in logistic regression, obviously your features input looks something like this. You have n patients by n features. Every feature has a beta that's learned for it, and those betas times each of those features values are summed up. Then a logistic transformation is applied. Your output is a probability between 0 and 1. So neural networks can be thought as people like them because they can self-learn a complex representation of the input data. And you can actually think of logistic regression as a neural network with no hidden layers. So you go straight from your input layer to your output layer, which would be the logistic transformation. Whereas in a neural network, you have hidden layers in between. And so when we just talk about popular terms, you have your hidden layers. Within those hidden layers, you have what's called neurons. In those neurons, you have activation functions. And these are just transformations of the inputs, which are the outputs of the previous layer. Similarly, you just have these beta learnable parameters and all these transformations. And different hyperparameters that need to be defined in training are things like your numbers of neurons, hidden layers, batch size and epochs, activation function, learning rate, regularization, etc. There are things that we have to be considerate of, especially in this data set where we had such a low percent of mortality, and also neural networks can overfit really easily since you have so many learnable parameters. So obviously things you could do are collect more data. In terms of collecting more data, our solution for that was you could do data augmentation, where we just augmented the number of positive training samples by adding Gaussian noise. So for the example of in-hospital mortality, it was a 0.81% occurrence. We augmented that by 100x. We have a 45% augmented occurrence. We also implemented things like early stopping, and early stopping is simply the process of during your training of your deep neural network, you just say like when your validation loss starts to increase compared to your training loss, you can stop training. We also implemented L2 regularization. L2 regularization is just when you penalize squared weights. The whole point of this is to just keep weights small. And the learnable or the parameter that you have to set for that is called lambda. We also implemented Dropout to help, and that's just when you randomly remove neurons during training. And the whole point of this is to really prevent neurons from co-adapting to each other. And then these are various ways to assess model performance. I won't go into them in detail, but in case someone wanted me to define them later. So yeah, we trained these different types of models. These are the final model hyperparameters that we ended up with for each neural network. And then in terms of model performance, what we saw is that, yes, the deep neural network and the logistic regression models both outperformed ASA. And on top of that, you can see that I've tried to highlight here the DNN, the best DNNs in blue, the best logistic regressions in orange. And overall, the DNN does slightly outperform the logistic regression. On top of that, obviously, we want to recommend some kind of threshold. So the best threshold was chosen as 90% sensitivity. And what we saw is that overall, the best DNN had the highest specificity and had 1,500 less false positives than the best performing logistic regression. And one thing so with that paper, we were like, okay, I think people are interested in some type of interpretability. So we did display some types of feature importance contributions. So for the logistic regression model, that would just be the learned logistic regression weights. And the top features that were learned for the logistic regression model were ASA, the presence of an arterial line, starting hemoglobin, minimum heart rate, and age. For the best DNN mortality model, what we specifically looked at was instead decrease in AUC. So that's, you could call that feature ablation. So every time we removed one of these features from the model, we looked at the decrease in performance. And so the ones with the most decrease in performance would be the ones that had potentially higher feature importance. So you can see they are different. So in this case, it was labs, ASA, anesthesia, blood pressure, and vasopressor administration. So then I'll go into just the paper that I was asked to talk about today. So that would be the development and validation of an interpretable neural network, and specifically focusing on just in-hospital mortality. So in healthcare, interpretable models are necessary. This is because clinicians like to understand the problem, and they also need to create targeted action plans. So you really need interpretable models to help gain the clinician's trust. So again, the reason why logistic regression models are so popular are that they're easy to implement, they're really easy to interpret, and they have good performance usually. But logistic regression can usually only impose linear relationships between the input and the target response. And we know that just in terms of clinical intuition and physiology and hemodynamics, the relationship between complications and physiology is not always linear. So as an example, I've just had here is that you can see that volume status, both low volemia and high volemia, can both increase your risk of postoperative complications. So we've already shown that deep neural networks can successfully predict post-op in hospital mortality with an AUC of 0.91. But one thing that's a negative about DNNs, at least in clinical medicine, is that they're often thought of as black boxes. And so a possible solution came from actually really reading this paper, and I was actually a journal club, I think, but Corona et al. Showed that generalized additive models with pairwise interactions, that he called them GA2Ms, can be applied to real healthcare problems with high accuracy. And essentially what he showed was that through just this visualization, an intelligible model like this helps clinicians to see new learned patterns. And the thought was, well, we can try to apply the same idea to neural networks. So we called it just a generalized additive model neural network. And so this was our proposed architecture. So we have our inputs. So this is our X1 to Xn features. So these were all of the continuous features. And for each of those features, we had essentially its own neural network. So they didn't have different numbers of hidden layers or neurons or anything. They were just repeats of each other. But so let's say for this feature, we looked at 1 to 4 hidden layers. We looked at 10 to 100 neurons per hidden layer. We looked at rectified linear unit or TANH activation for each of those neurons. And once those hidden layers, the last hidden layer outputs to a TANH activation layer with just one neuron, we chose TANH so that the values would be between -1 and 1. So similar to, when you would do some kind of like Z-score normalizing of your data. And on top of that, we have, so this is true for all of the continuous features. And then for the binary features, so as an example, like whether or not the patient had an arterial line, that was just a binary feature, a yes or a no. So those ones actually just went straight into a concatenation. And so we decided like then this layer, you could call that the learned function of each feature and each feature's values. And then that concatenation feeds into a logistic output, and those learned logistic weights of each feature, that multiplied by the learned function of each feature can be thought of as the learned contribution to risk of in-hospital mortality. So with this data set, the only difference here from the previous work that I was showing is that we did add 33 additional features. And specifically, these were the HCUP code descriptions. We selected 33 out of 183 just based on which ones were present on more than 1% of the total data. For those who aren't familiar, HCUP are diagnosis codes. And the final model parameters and results look like this. So with the HCUP features and without, you can see that they're actually pretty similar, except the L2 regularization number that was best was slightly different. And the feature set and model that did the best in terms of AUC was the generalized additive model neural network with HCP features with an AUC of 0.92. But then you can see that the average precision is slightly lower. And so it's only slightly higher in AUC, slightly lower in AP. And so overall, you could say that they're pretty similar. And you can see same thing if you look at their AUC, their ROC curves and their precision recall curves, they're relatively similar. And so, I mean, the whole point of this was really just I think we already knew that logistic regression and neural networks were going to perform really similarly, but so what we were really interested in was the visualization aspect. So this is a sample of the 9 continuous features that had the highest mean mortality risk in the GAM-NN, so the generalized additive model neural network contributions across all of the training patients. And so you can see that, and just to note, the more negative the contribution value, the less positive contribution it has to the predictive risk of mortality. And in blue is the neural network contribution, and in green is the logistic regression contribution. And overall, you can see that the direction of the learned contributions between the logistic regression neural network models were similar for these ones. So as in one is decreasing, this is also decreasing. And also the other interesting aspect was that there are still some where they learned different relationships, but also you can see that the GAM-NNs learned unique nonlinear relationships for each feature. It's not just a straightforward linear relationship. And so if we just zoom into one of them specifically, this is looking at the average mean arterial pressure for the last 10 minutes. You can see that, again, just highlighting that logistic regression learns just a linear relationship. As MAP increases, contribution to the risk of mortality increases. And if you look at the GAM-NN, it learned this, that in blue, you see that it learned this nonlinear relationship where it shows that lower MAP and higher MAP actually contribute more positively to the risk of mortality than the middle area. And so it learned this interesting nonlinear relationship, but the other thing is you can see this as helping with maybe a data-driven interpretation to clinical practice. So the learned relationship here can also indicate that there is potentially a target range for MAP. So in this case, 50 to 75, just because that's kind of maybe where the inflection points are, you could argue is maybe some kind of target range that MAP should be kept in. The other thing is that GAM-NN does definitely learn relationships that can reflect the distribution of the data set. So you can see here, so this is a typo, it should be Ames case hours. So this is the total case hours that were spent under anesthesia. And you can see that, interestingly, what's learned is that And same thing with logistic regression. You can see that, right, the less hours spent under anesthesia contributed more positively to mortality risk with an inflection point around 5 hours. And this is maybe counterintuitive, since you would think like longer case hours is longer case hours is higher risk type of surgery. But this might be explainable just by the fact that extremely high anesthesia case hours are pretty infrequent. And so not all in-hospital mortality patients are necessarily going to spend significantly longer amounts of time under anesthesia. And similar to logistic regression, you can provide patient-specific interpretability now, since we have the individual feature contributions. So if we look at the top 10 neural network contributions that were learned from the best performing model for 2 different in-hospital mortality patients from the test set, you can see they are, it's just interesting to have. So as an example, in this patient, the highest contributor was the presence of an arterial line, followed by their ASA score value, their minimum diastolic blood pressure, their age, and their average diastolic blood pressure. Versus in patient example 2, you can see that the fact that they were in category 1 of HCUP diagnosis codes contributed the most. And then, yes, still the arterial line presence, then the minimum diastolic blood pressure, minimum hemoglobin, then the ending rate of phenylephrine. So it's just an interesting way to show to the clinician what contributed the most to an individual patient. So in conclusion, just modern medicine definitely requires tools to change from more reactive patient management to a more prospective or proactive approach, but that these approaches definitely need to be accurate and interpretable. There are 2 ways to approach potentially this type of prospective healthcare, just a general patient risk score to allocate resources, or you can have something like an acute event risk score to avoid causes of complications altogether. And we did show that DNNs can perform with high accuracy when compared to currently used risk scores for adverse outcomes. Logistic regression does perform comparably for many of the problems, and that's actually to be expected, especially when we know neural networks where they really outperform is when they have more complex data. This data itself is probably a little bit simple for the DNN, so logistic regression is able to learn pretty well. But logistic regression does have its limitations. It's a shallow model, has no ability to create new feature representations on its own. It can only combine those features linearly. Any kind of nonlinear feature representation has to be done manually. So we proposed the GAM-NN to learn those nonlinear patterns in the data, and it seems like maybe it resembles more of clinical intuition without any extra featureization. And the proposed GAM-NN here can be interpreted pretty easily while maintaining the model performance. Obviously, there is a limitation. We might have limited generalizability in this model just because it was only looking at data from a single institution and also only looking at data from 2013 to 2016. And we know that we know that just clinical practice from institution to institution is not only different, but also medicine changes on a yearly basis. So there's some, limited generalizability potentially there. And the last thing just to highlight is obviously interpretability is not necessarily causation. So in the feature contributions, just because the patient had the highest feature contribution was the presence of an arterial line, does not necessarily mean that the removal of not giving an arterial line means that the patient would not have died. That's definitely some caution has to be placed there. And so, yeah, with that, I'll just kind of open up the floor to any questions.